All right, welcome, ladies and gentlemen. There is an overview of our upcoming chapter. This will be our last chapter before the semester ends. We plan on getting all 5 of these sections done with a test and a couple quizzes throughout. So you'll kind of take a look here. We're dealing with exponential functions and logarithmic functions. So the first 2 sections, we're going to be looking at just the basics of them, and what they are, what they look like, what their graphs look like, and that sort of things. Then we're going to be looking at the properties of logarithms. Then we're going to be solving exponential and logarithmic equations here in section 4. And in section 5, we're going to be dealing with real-life situations. That's what it means by models usually. Really, the bulk of everything will probably, the graphing, yes, very important. Understanding logarithmic exponential functions. But what ends up being kind of the big pieces here, I think, are 5.3 and 5.4. They're usually the most confusing ones, too. All right, so this is going to take a lot of work for you guys to make sure we end the semester on a high note. So let's go ahead and get started here. So 5.1 are exponential functions and their graph. We're going to be looking at domain, a little bit at range, a little bit at domain. Really, we want to look at what is an exponential function and what does their graph look like. And you can kind of see that little picture there, what they might look like. All right, so the exponential function. This is any function in the form y equals a to the x. What you need to pay attention to is this is kind of a new function for most of us. This x is in the exponent. Notice most of what we've been doing, like y equals x to the third. This x was actually the algebraic piece, the base here. This is base x, by the way. Whereas now we're going to look at something like this, 3 to the power of x. And for the most part, we're going to be plugging in numbers to figure out the y values so we can graph them. But let's take a look at what all this stuff is. So first of all, a has to be bigger than 0, and a cannot equal 1. If a is 1, then it's just a boring function. And a is not negative because it gets weird stuff if a is negative. You can put a negative in front of the a, but a itself is not negative. And then x is any real number, which actually tells you, by saying that x is any real number, that tells you automatically the domain. That means I can plug anything into this function. There's nothing I can't plug in. So the domain is all real numbers. And for our parent function, the basic function a to the x power, the range is all positive reals. So we would look at this. So from 0 to infinity for the range, whereas domain would be negative infinity to infinity. We have this thing called the initial value. And the initial value is when x equals 0. So it also means it's the y-intercept of our graph. Because usually these are real-world examples and real-world problems that could happen, initial just means when time equals 0. So time is our variable. So in this case, it's when x is 0. All right, so we're going to be looking at all sorts of stuff in this particular form, a to the x. We're going to look at 3 to the x, 2 to the x, 1/2 to the x, 2 to the negative x, that sort of stuff. So let's look at, first of all, the basic graph. Now, what you'll notice here is this is going to be the basic graph, and this is kind of like, quote-unquote, the basic graph. 2 to the x is not the parent function for all functions, all exponential functions. We kind of think about it as 2 to the x is the parent function for all that has the base of 2. And then 3 to the x is the parent function for all of the ones that have base 3. So it all depends on the base as to whose parent you're looking at. So let's take a look at this particular function, this graph. I said the range is above the x-axis, so I'm not going to worry about any of those. Oops, not negative 2. Well, with any new function, we always start with a table. And for the most part, that's probably where most of you want to go. And for the basic function, notice there's nothing going on in front of the 2 or after the x or after everything. We're just going to use -2, -1, 0, 1, and 2. Now, let's start with the easy ones. What happens if I plug 2 to the second power? Well, that gets 4. 2 to the first power is 2. 2 to the power of 0 is 1, as is everything. And then we get some hard ones here. So 2 to the negative first power. The negative exponent tells me to find the reciprocal. So this becomes 1/2. 2 to the -2 tells me to find the reciprocal and take to the second power. So it's 1/4. All right, so let's get some numbers on my y-axis. I didn't put them on there for a purpose because I needed to know my numbers first. I'm going to go ahead and plot my dots. So 0, 1, that would be my initial value. 1, 2, and 2, 4. And half at -1 and a fourth at -2. And then so on, you'd get to an 1/8, and then a 16th, and a 1/32nd, and a 1/64th. And you'll never actually reach 0. There's no way it's ever going to reach 0. So in this particular case, we do have actually a horizontal asymptote. We have a horizontal asymptote at y equals 0. No vertical asymptotes, but if you go to 3, you're going to get an 8. If you go to 4, you get a 16. And it just grows really, really fast. If you've ever heard the word, oh, that's going to grow exponentially, that's dealing with these type of graphs. It's a growth. And by the way, I'm going to mention this now. This is a growth model. Because as x goes positive, or as x gets bigger, y gets bigger. That's a growth model. We have decay models as well. You're going to get an example here in a moment. All right, so that's 2 to the x. Why don't we try 4 to the x? So same idea. And again, because there's nothing going on, I'm just going to go -2 to 2. Now, I'm going to scale my graph correctly here, but if I did my table again, I know if I plug in 0, I get 1. Plug in 1, I get 4. Plug in 2, I get 16. -1, I get 1/4. Plug in -2, I get 1/16. So that means I'm just going to make my scale here as 4s so I can plot my dots. All right, see how easy this is, especially for the basic functions. You guys shouldn't have any problems graphing these particular functions. There's 0, 1, 1, 4, 2, 16, and then a fourth, then a 16th. Obviously, you get so close to the x-axis, it's hard to graph. But you'll notice that I don't ever cross the y-axis or the x-axis here because this still has that horizontal asymptote because there's no transformations going on, no translations. All right, so this is a growth model, and it has everything to do with these numbers here because 4 is bigger than 1, and so is 2. That makes it a growth model. So what's going to happen if I do this? 2 to the -x power. So let's see what happens here with this particular function. We make our table. Go -2, -1, 0, 1, and 2. Well, 2 to the 0 power, that's still going to be 1, so that's nice. And then if I plug in x equals 1, that becomes 2 to the -1, which is actually 1/2. When I plug in a 2, I get 2 to the -2, which is 1/4. Plug in a negative 1, that becomes 2 to the first power, which is 2. And then plug in negative 2, I get 2 to the second power, which is 4. So it looks like I need the same type of numbers here as I had before, 1, 2, 3, and 4. But see what happens here. When I plug in negative 2, I get 4. When I plug in negative 1, I get 2. And then downwards in this fashion, again, horizontal asymptote. And some of you might be looking at this, will go, well, that 2 and that 2 should have been a growth, but this is actually a decay model. This is a decay model because it's actually decaying as time goes forward. And the reason for that is because if you use the negative exponent, I could say 2 to the negative x is equal to 1 over 2 to the x, which is actually equal to 1 over 2 to the whole power of x, because it'd just be 1 to the x power. So this is actually a 1/2 to the x. So these two statements here are identical. 2 to the negative x is the same thing as 1/2 to the power of x. And you'll notice this 1/2 means it's cutting in half each time as you go forward. We call this actually a half-life model in chemistry, or a basic half-life model. One more quick example. I want to do the other one with the 4. You might understand where this is going here. I'm going to try to do this with one without a table. Okay, no up and down shift, so it still has a horizontal asymptote at 0. I'm going to use my same numbers as I did before, because it seems like I should, right? And then if I plug in a 0, I get 1. If I plug in a 1, I get the reciprocal to get 1/4, 1/16 over here. And then backwards, negative 1 will actually get me the 4, and negative 2 will actually get me the 16. And sure enough, we get this decay model again. And my graph is kind of ugly because of the pen here, but I think you get my idea here. This is a downward trend. This is a decay model as well. You guys deal with these decay models a lot in biology, or growth models in biology, because population grows at an exponential rate or decays at an exponential rate. And you guys deal with a lot of population in biology. All right, so that's the basic graph, and we can change these graphs using all of our transformations that we've learned throughout the class so far. We have up, down, left, right. We have dilations of both directions, x and y. If I was to give you something like this, 2 to the x plus 1, well, the parent function would be y equals 2 to the x. But in this case, we're adding 1 to the x value. That 1 is in the exponent, which means that is a left-right shift. And because it's plus, it means I'm going left 1 unit. So we could take our 2 to the x function, which is something like that, and we could shift it to the left 1 unit and get something a little bit like this. It also kind of looks like it got shifted up, but in this case, it's a left-right shift. Even though there are ways we can make it look like an upshift, but we're not going to deal with that right now. What about this one? Y equals 2 to the x minus 3. So in this case, we have a minus 3 that's going on outside the 2 to the x. Again, this is 2 to the x being our parent function. This would be a downward shift down 3 units. So likewise, we would take our, let me get rid of that there. We would take our blue function there, which is 2 to the x, and we would just move everything down 3 units. So there's 1, we'd come down here and look like this. Notice the function still looks exactly the same. The horizontal asymptote, by the way, would also move down 3 units to -3. The y equals -2 to the x power. This is a negative in front of the function, which means it's a reflection over the x-axis. So we would take 2 to the x, and we'd reflect it across the x-axis. And that's kind of the reflection we'd have. We would never call this a decay or a growth model because it's not above the x-axis. We don't care about things, or we don't name this particular function below the x. And then we have this one. This is y equals 2 to the -x. And since the negative is with the x, this is also a reflection. This is the one that people forgets. It reflects over the y-axis. And if we think about this being 2 to the x, 2 to the -x would be this. It's reflecting across the y-axis. Notice I made sure I intersected at the same point. This would be y equals 2 to the -x. All right, so all of our properties still apply here. With the x means left and right. Outside the function means up and down. And likewise with the negatives. All right, I didn't say anything here because I wanted you to actually try to read that number in your head. Or, sorry, not that number, this name right here. This is actually a mathematician's name, and it is not pronounced Euler. It is pronounced Euler. Kind of the best way to write that word. He was one of our great mathematicians way back when, and he's actually attributed to what's a word for it? Really figuring out a lot of math, a lot of hard math that we actually take for granted now. And one of them is Eulers Number. Even though he didn't invent this number or find this number, it's attributed to him because of how great he was. And Eulers Number is the number E. And some of you are like, well, E is not a number. But it is. Just as pi is a number, pi is actually a Greek letter. And you've probably seen them in my classroom. Pi is the Greek letter, so it's actually an alphabetic letter. But we know that this is actually 3.1415926535889, blah, 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 right? We know, and I know all of you knew those decimals too. We know that that's the equality, or almost equality, and E is kind of the same type of number. And you can find this number on your calculator. It's going to be probably e to the x or something thereof. And when you plug that into your calculator, you're going to get e caret something. And if you want to make sure for yourself, you would just plug in a 1, because I'm going to say e to the first power is 2.7182818288459, and it keeps going forever, just like pi. These two numbers are actually kind of similar. They're called transcendental numbers. They're not irrational numbers. Well, technically they are, but they're not irrational numbers. They're not rational numbers. We call them transcendental because they kind of don't follow very many rules. However, E is super, super important to us, especially in harder math and the particular using of E as a base number, and calculus. It's super handy. Where else is it handy? Oh, it's handy in what we're going to be doing here shortly. We're going to be looking at money problems. And money problems, E is very important because if you didn't have E, you wouldn't be making as much money in your bank. Not that you make a lot right now anyway, but... All right, so E, if we were to look at the graph of E to the X, it's going to look really a lot like everything else. Because it's still an exponential function. E is just 2.718. And if we were to plot some points here, I would still go through the point 0, 1. And then at the point 1, I'd be at 2.7, which is right in here somewhere. And at negative 1, I'd be a little bit less than half, so somewhere in there. And the function is still going to follow the same outline as before. We still have a horizontal asymptote at 0. All right, so that's E. Don't think I'm just skimming over this because it's just a little brief piece. E's going to come back up here in just a couple minutes here, don't worry. So what I want to look at now is where can we use this stuff? Where can we use exponential functions? And for the most part in math class, we like to first introduce exponential functions with the study of interest and interest rates. So what we start off with is a basic interest formula. And this is saying, let's say you wanted to put money into a bank and the bank is going to give you money compounded every month. So that would be compounded in times per year, where in is just a number. So if I would say compounded every month or monthly, I would say 12 times per year. We're going to look at a relatively simple formula here. And I didn't put it on here, but the equation is usually equals to A. And I always say A is the amount in your account. So it's easy to remember. But really the bulk of this for us right now is P equals 1 times R over N to the NT power. So notice we have an exponent here, so this is important for us. That's why we get exponentials. Now, be important to know some of this stuff. P is what we call the amount you invest. It's actually called the principal. So the P is your principal, P-R-I-N-C-I-P-L-E, not A-L. It's the amount you invest. It's the amount of money you put into the bank account or you put into the bonds or whatever you're doing. R is your rate as a decimal, obviously. N is the number of times compounded in a year. So if we say monthly, then it's 12. If we say yearly, then it's 1. And actually that's good because if it's yearly, then it's 1, and it actually gets rid of these n's basically. And T is the amount of time in years. However, we have a different formula as well, and this is where you have to distinguish between the two. So notice the difference between these two things. Interest compounded in times per year. That means once a month or once a week or once a day. Whereas continuously compounded means it's always compounding. And when it's always compounding, we don't know what n is, because n would be infinity. And that doesn't really make any sense. So continuous compound interest actually gets a much simpler equation. The P is still the same value. I always call this A PERT, by the way, because it's pretty easy to remember that. P is still principal. It's the amount you invest. R is your rate as a decimal. Duh. And T is the time in years. Notice I don't have to deal with anything else. That's all. If I know my principal, my rate, and my time, I can figure out how much is in my account using this very simple formula. Most of you will probably memorize this continuous one before the other one. So let's go ahead and use both of these formulas in a single question. So a total of $12,000 is invested at an annual interest rate of 9%, and I want to find the balance after 5 years if it is compounded first quarterly. So that means it's not continuous. So that means I want A equals P times 1 plus r over n to the power of nt. So let's plug in what I know. A equals the amount I invest. Okay, that means that's 12,000 times 1 plus my rate. Rate is 9%, which is equal to 0.09. So it's 0.09 over quarterly. Quarterly means every 4 months, or sorry, every 3 months. And well, quarterly obviously means 4 times a year. So it's 4 times a year. My N is 4. My T is 5 years, so it's 5. And if I plug this into my calculator, which I'm doing right now, I get 12,000 times 1 plus 0.09 divided by 4 to the power of 20. I get, at the end of my time, at the end of 5 years, I now have $18,726.11. But let's see what happens if I change this quarterly to monthly. Now, it might seem in your head that it should just come out to the same number because I'm doing it over the same amount of time. But let's see what happens here. 12,000 times 1 plus 0.09. A lot of this is still the same. But in this case, monthly means 12 times a year. So I'm going to go back in and I'm going to change some numbers in my calculator. So instead of dividing by 4, I'm going to divide by 12. And instead of to the 20th power, I'm going to go to the 60th power, because that's 12 times 5, by the way. And you notice here, I get $18,788.17. Now, some of you are like, well, that's not very much. It's only $62. But $62 could be quite a bit after an amount of time. If you put in $12 million, that would be like $26,000, $22,000, or $62,000, sorry. All right, so again, let's change how it's going to be done. We could do daily, by the way. If you wanted to, you just put 365 in for 12. But let's do the continuous compounds. So A equals P times E to the RT power. So A equals, we still have 12,000. Let's see if this gets me any more money. Compounded continuously. You might be thinking that it does, but you don't know until you do it, right? 12,000 times E to the 0.09 times 5. Let's see what we get. Here I get $18,819.75. So notice it's actually a good thing to have continuously compounded interest. Notice I've made, compared to quarterly and continuous, I've made what? Almost $93 more over 5 years. Yeah, it doesn't sound like a lot, but again, it adds up. All right, so that concludes this first lesson. Doing this video very early so you guys can get a jump start. You have 7 assignments due, or 7 problems due to me. This is Monday's, what is that? That would be November 30th already. Last day of November. That's when we're working on this. All right, guys, have a great weekend. I will see you guys on Monday.